Hi everyone! In this video, we are going to learn about the undefined terms of geometry, as well as how they can be applied to other definitions, and some basic postulates that help us apply these terms to understand the relationships between figures in geometry. Our first term is a point, and a point indicates a location and has no sides. So we might represent that with a dot and then a capital letter to name it. So I could have point A, I could have point Q, I could have point Z. You notice that every time I do put a dot, and although these dots do technically have size, we work with the understanding that a point is actually infinitely small and has no size. Our next definition is a line, and a line is a straight path that extends in two directions without end. So you notice that I put arrows on the end to show that it does extend in both directions. If I did not put arrows, we might assume that it stops. And you can name a line by any 2 points that are on the line. So if I put some points here, I could have A and B, and we could name this point C. I could name this line AB with a line symbol over the top. I could do line BC. You notice that it doesn't matter that C is on the right and B is on the left, because there are 2 points on that line, and it does not matter the order that we go in. So I could also use line AB. But every time that I do that, I am drawing my line symbol on the top, and I'm making sure to draw those endpoints. The other thing that I could do is if I had a letter on the edge of it, like an L, and you notice that I'm doing a lowercase cursive letter. I'm just using cursive to make it really clear that it's not a point. I could name this line L, or L with the line symbol over the top. And with any of these terms, I could also name it line AB. And this is very helpful if you are typing out the words instead of drawing them, because then you don't need to try to make that symbol. These are all acceptable ways to name these lines. Our final undefined term is a plane. And a plane is a flat surface that extends in without end. So just like a line is infinitely long, a plane is infinitely big, but in 2 dimensions instead of 1. So I could show a line, or I could show a plane by drawing something similar to a parallelogram. I like this drawing a parallelogram because it gives it an angle rather than trying to draw a flat surface on a flat piece of paper. And to name it, once again, we could use a cursive letter, but this time it would be a capital letter. So I could put a P in the corner and name it plane P. Or I could put some points on it. And as long as I have at least 3 points that are not on the same line, so I could put point A, put point B, and point C, I could name it plane ABC. We don't really use symbols for planes, we just write the word out. Now it is really important that those points are not on the same line. If they were on the same line, we would have something like our line above, and you wouldn't know exactly which plane I'm talking about. Next, we have a line segment. And a line segment is a part of a line that has 2 endpoints and every point in between. So now to show my line, I'm actually drawing points on the end instead of arrows. And if I name those points A and B, then my line segment would be AB with a segment symbol on top. You notice there are no arrows because this is not going on infinitely in both directions. Now line segments are different because you have to name them by the endpoints. You can't name them by points in the middle, or else you're talking about that shorter segment. A ray is a part of a line that consists of one endpoint and all the points on one side of that. So if I have endpoint X here, and then this is point y, I'm starting at point x and then going in the direction of point y infinitely, and I'm going there infinitely long. So I could name this ray x, y, and then I put a ray symbol. How many arrows do you think are going to be on a ray symbol? It's going to have just one to show us that it does extend, but only in one direction. One key fact about rays that we're going to use in this class is that even if I were to draw my ray like this, even if I were to draw it like this, and I named this point A and this point B, I would not do this. That's a big no-no. I would have to start at my endpoint A and go in the direction of B. So you always write the endpoint first, even if the ray is going in a different direction. Our last two figures that we're going to learn, we have opposite rays. So opposite rays are two rays that share an endpoint and extend in opposite directions. So maybe they share point X, this is point Y, and this is point Z. Then I would have ray XY and ray YZ. And what do you notice? Oh, wait, that was totally wrong. I'm going to have ray XZ because they have the same endpoint. So it'd be ray XZ. So even though ray YZ goes in the same direction as XZ, I have to use X because that is the endpoint that they share. Now, what do you notice about an opposite ray? What figure does it actually make? An opposite ray makes a line. It's just being named by the two rays that make it up rather than just any 2 points on that line. Our final structure we're going to learn is an angle, and an angle is the space between two rays that share an endpoint. So if I draw two rays that maybe share the endpoint X, and this is point Y, and this is point Z, my angle is this thing in the middle. It's this space between it. And I could name this angle a couple ways. I could just call it angle X. And you notice that angle X is not actually it's not a less than symbol, it's an angle symbol, which is just pointed down a little bit. So I could name it angle X. But sometimes we have angles that are next to each other, and X won't be descriptive enough to tell your reader exactly which angle you're talking about. And in that case, we're going to use 3 letters. We start at point Y, we go down to X, and then up to Z. And you could also go the other way around. So I could have angle Y, X, Z, or angle Z, X, Y. And in both of those cases, point X in the middle is our vertex. You always put the vertex in the middle. So if you want to be safe, always name an angle with 3 letters, and that way you can prevent any confusion. Our last 2 points. We have the adjective collinear and the adjective coplanar. I want to specify that these are descriptions of points. They are not an actual figure in itself. Collinear, that word co, or that prefix co, kind of like the word company, they come together, right? So they are on the same line. Coplanar has that prefix co again, but then we see the word plane. So it's points that lie on the same plane. So if I ask you for a set of coplanar points, you're going to give me points that are all on the same plane. So now let's think for a moment. We have some different ways to name lines. So we could name lines by the lowercase letter that names it, or any 2 points on the line. The order of the points does not matter unless you are naming array. So in array, the order matters, but in lines and line segments, it does not. Don't forget to use your line symbol when writing lines. A lot of geometry is about the details and the notation that we use. So you need to make sure that you are using the correct notation so your reader is not confused. Remember, collinear and coplanar are both adjectives. They are not a type of shape, they are describing the figures in your shape. Remember that to make a plane, the points cannot be collinear. The last thing we're going to talk about in this video are our 4 postulates. Our 4 postulates are the types of, they are the facts that tell us how things interact with each other. Now, all you have to know about the word postulate for right now is that it just means a fact. We will talk more in later videos about what is the difference between postulates and other types of statements that we learn. So for postulate 1, through any 2 points, there is exactly 1 line. So if I give you 2 points, point A and point B, everyone would draw the exact same line, because I can't give you something like this, right? That does not make sense because those lines will not go through both points. You need the line that actually connects them, like this. The next statement, which makes sense, is if 2 lines intersect, then they intersect at exactly 1 point. So if I have a line here and any other line that I draw, it's going to intersect, and it's going to intersect in exactly 1 spot. Now that's not to say that every pair of lines intersects in the same spot, but it will be exactly 1. If I tried to show anything else, I would end up drawing a curved line, which we're not allowed to have. The next one looks a little bit weirder. If 2 planes intersect, then they intersect at exactly 1 line. So think if I have a plane going this way, and then another plane like this, they're going to touch right here. And that is a line. Now you might say, but that looks like a line segment. It doesn't go on forever. It doesn't have any arrows. And that's where you need to remember that planes are infinitely big. We just can't really draw that well. So this line does actually extend this way and does actually extend that way because the planes extend those ways. You have to keep that in mind. Even though it might look like a piece of paper, in the picture that you're making in your brain, make sure that you're imagining that paper going as far as you can see in every direction. And our final postulate, through any 3 non-collinear points, there is exactly 1 plane. So that only is true if you had points like this, right? If you had 3 points that were non-collinear. Collinear points would look something like this. And in this case, you would not be able to draw a single plane. Thank you guys for taking the time to watch this video. In my next video, we'll be going through some examples about how we can use these terms and postulates to answer some problems.